everyone. In today's video, we are going to learn about noise in FM receiver. So let's begin today's video. So our topic is noise in FM receiver. The block diagram for the same is shown here in the picture. That we transmitted an FM signal, in which the noise gets added in the channel, which is a white noise having a power spectral density of N0/2. So at the front end of the receiver, here at this point, we receive a signal which is S of t plus W of t, means the FM modulated wave and a white noise, which is a wideband noise. Then this signal is passed through a band pass filter, which passes the modulated signal as it is without any distortion and narrow band this noise W of t to N of t. So output of band pass filter, which is represented with X of t, is nothing but S of t plus N of t, where N of t is my narrowband noise. Then the next three parts are the components of a frequency demodulator, in which the first block is limiter, the second block is a discriminator, and the third block is low pass filter. So let's see the function of each block. Limiter. What a limiter does. Friends, as we send a FM wave, the noise gets added. So in FM, our aim was the frequency should be varied according to the modulated signal, but amplitude remains constant. But what happens when we actually receive the signal? The amplitudes are also being varied, right? This is due to the noise. So what a limiter does, limiter first changes this signal, the variation in amplitude signal, it clipped off the signal like this and produces a rectangular pulses of varying frequency and constant amplitude, right? So now the amplitude of the wave is constant. The second integral component of this limiter is a band pass filter. The second component which is integrated with this circuit limiter is a band pass filter. What the second component does, it changes this rectangular pulse to a sinusoidal waveforms of constant amplitude. Means at the output of the limiter, we get a pure signal like this, frequency modulated signal, which is a sinusoidal signal of varying frequency, right? The next part of the block is a discriminator. Discriminator contains two parts. One is slope network or differentiator, and the second is envelope detector. To understand the function of discriminator, suppose our modulated signal was a purely frequency modulated signal, right? The equation of frequency modulated signal is nothing but AC cos omega ct plus kf integration 0 to t m of t dt. This is the equation. Now if I differentiate this equation, what will I get? I will get AC cos omega ct as it is into omega c of t plus kf m of t, correct? Now you can see that this equation S dash of t is a hybrid modulated wave, in which this equation is for frequency modulated and this is for amplitude modulated, right? So we get the equation which is a frequency modulated as well as amplitude modulation. Now the second part of the envelope detector, second part of discriminator is envelope detector. Now what is the function of envelope detector? We have seen in earlier videos that envelope detector detects the variation in the amplitude, right? It traces the amplitude. So here the envelope detector finds the amplitude of this waveform, the amplitude of this waveform. Then what was the last part of the block diagram? Was a low pass filter. Then the whole signal is passed through a low pass filter to get final output y of t. Now we have to see at the output of y of t what is the signal strength and what is the noise strength. Right? Then only we can find the figure of merit. So friends, before finding the signal to noise ratio at the input, let's first analyze the circuit. Okay, otherwise it would be complex to understand. Let's see. See friends, the filtered noise n of t is a narrowband noise. If it is a narrowband noise, we can represent it in the in-phase component and quadrature components. Right, so I can write this n of t as ni of t cos omega ct minus nq of t sin omega ct. We have already seen this in previous videos also. Now, if we may express this n of t in terms of its envelope and phase, right? So I can write n of t is like r of t into cos omega ct plus phi of t, where r of t is nothing but under root ni of square t plus nq square of t. Right, I can write this r of t in terms of ni and nq. Then what is psi of t? Psi of t, the phase difference. I can write this phase as tangent inverse nq of t by ni of t. Right, I hope I am clear up to here. This equation is important. We are going to use this equation further. Right, n of t, r of t is equals to r of t cos omega ct plus psi of t. Right, we should know the value of r of t and psi of t. The next is that are modulated signal. What was the equation for modulated signal? I may keep it encircled so that it is easy to use further. Now my s of t is, it is ac cos omega ct plus 2 pi kf 0 to t m of t dt. This is the equation of fm. Right, this is the equation of fm. Now if I have to represent this equation like in terms of like we represent noise, I can write s of t equals to ac cos omega ct plus phi of t, where phi of t is nothing but this factor I have written here. Phi of t is equals to 2 pi kf 0 to t m of t dt. Right, now output of the band pass filter, moving back to the block diagram, output of this band pass filter x of t is s of t plus n of t. Right, so I can write my x of t is s of t plus n of t, modulated signal plus narrowband noise. If it is the equation, I can write s of t as cos or ac cos omega ct phi of t plus n of t we represent here r of t into cos omega ct plus psi of t. Right friends, so if I have to represent this in the terms of phasor, how could I represent? Let's see. Suppose this is my zeroth reference. Okay, this is zero origin reference. Now first equation is ac cos omega ct plus phi of t, means this, if this angle is phi of t, this small angle is, this angle is phi of t, so this phasor must be ac cos phi of t. Right, the second thing is r of t cos omega ct phi of t. So if my r of t is this r of t, so its angle is phi of t with respect to origin. Right, so if I draw a parallel line with respect to origin, so this angle is phi of t, this angle is phi of t. Correct. So what would be, if I extend this ac to further, this angle would be phi of t This angle would be psi of t minus phi of t, right? This angle psi of t minus phi of t, right? Now if I draw a perpendicular to this line, this is a perpendicular, right? So this term, this is r of t, so this term becomes r of t sine theta, and theta is psi of t minus phi of t, and this becomes, this extended line becomes r of t, this r of t hypotenuse into cos theta, and theta is again psi of t minus phi of t. Correct, friends? Everything is clear? Correct. So I can write theta t minus phi of t, this is theta t minus phi of t is how much? This is my theta t, resultant vector का जो theta था, this is my theta t minus phi of t. This is equals to tangent inverse r of t sine psi t perpendicular upon base. Perpendicular is r of t sine psi t minus phi t upon AC plus this extended value r of t cos psi t minus phi t. Right? Tangent theta is perpendicular upon base. I hope I am clear up to here. Okay, let's move further. Now my AC is very large in compared to the second factor. My AC is very large in compared to this factor, so I can write this theta t minus psi t is equals to tangent inverse r of t sine psi t minus phi t by AC. Now we know that this factor is less than 1. Why? AC is very less, AC is very large. When AC is very large, then we know tangent inverse theta, and theta approaching to 0 is equals to theta. So I can remove tangent inverse from here, and I can write as r of t sine psi t minus phi t by AC. It is equals to theta t minus phi t. Correct? Now I can write theta t is equals to psi of t plus r of t sine psi t minus phi t by AC. Now what was my, see, what is my phi of t? If you remember, or I'll show you again, what we assume phi t was 2 pi kf integration m of t, right? Putting here theta t is equals to phi t. Phi t is nothing but 2 pi k integration m t. I am supposing this factor as my quadrature component of, this is quadrature component of noise. You should see this. This was what? This is the this was the phasor, and this was in phase component, this was quadrature component. So r of t sine psi t minus phi t is quadrature component of noise. Right, so I can write phi t plus quadrature component divided by AC. I hope I am clear up to here. See friends, if you have any doubt, please send it in the comment section. I'll revert to that. Okay, moving next. Now this signal is passed through, this is the output of band pass filter. Now this signal is passed through a limiter which removes the variation in amplitude and produces the waveform. Then that signal is passed through a discriminator, right? What discriminator do? It first differentiates, right, and then envelope detection, right? So now this signal, when this signal is passed through discriminator, what will be the output? V of t is integration of 1 by 2 pi d theta dt. Now my V of t would be 1 by 2 pi d by dt, this whole equation, correct? V of t becomes 1 by 2 pi, से 1 by 2 pi cancel out, kf m of t integration and differentiation plus this factor is assumed to be a derivative noise term nd of t. Now we have to see what this term is. Correct, friends? frequency. Now my derivative noise term is nothing but the 1 by 2 pi derivative term. If I see, it is 1 by 2 pi AC, this AC, d by dt, nq of t, and nq of t is rt sin psi t minus phi t. Right, now we know that the term is additive noise. Okay, now suppose what is the meaning that I am sending nq of t to a differential circuit which is having a transfer function d by dt 2 pi ac d by dt and producing a term nd of t. Right, this is the meaning. Now we know that the differentiation in terms of frequency, we can write jf by ac, 1 by 2 pi से 2 pi cancel, jf by ac. AC is the constant. Now if the power spectral density of nq of t at the input is snq of f and the power spectral density at the output is snd of f, then how they both are related? They are related with this formula we earlier discussed. Snd of f is mod hf square snq of f, right? Then I can write this, my snd is f square by ac square snq of f from frequency range minus b by 2 say b by 2. Correct? Now we have to find the signal to noise ratio, the main important function of the receiver. Now see, now signal to noise ratio, this is the equation for frequency modulated waveform. Correct. What is the signal power here? The signal power here is AC square by 2. AC square by 2. And what is N naught into W? If I have to calculate noise power, it would be, we were writing that the noise spectral density is N naught by 2 and the bandwidth of the filter from minus b by 2 to b by 2. But what actually happens is, in the previous cases we assumed that our bandwidth by 2 was equals to fm, right? But now my bandwidth by 2 is much greater than fm, so n naught by 2 is 2w. If I have plot here, this was the bandwidth, but in this cases I am assuming that my bandwidth of signal is from minus fm to fm. So minus fm to fm, or I can say minus w to w. Just a minute, I'll show you. Previously what we were doing, we were assuming that my minus b by 2 to b by 2 is my transmission bandwidth and it is equals to fm, right? But in this case my fm is less than my b by 2, so fm or w, message frequency, so this time this b becomes 2w, right? So I can write the noise power becomes n naught into w, and this is my signal to noise power. Similarly, in the if I have to calculate output signal to noise ratio, it is kf square into p, right? See, here If P is the average power, if C here, if C is the average power of M of t, P is the average power of M of t, the average power of signal in this component becomes Kf square into P. So I am finding it is Kf square into P. If I have to calculate noise power, it becomes N naught by AC square F square dF minus W to W, right? So it becomes 2N naught 3 AC square W cube. So signal to noise ratio at the output is can be found by dividing these two equations. Then what is figure of merit? Figure of merit is signal to noise ratio at the output to the signal to noise ratio at the input. Finally, you get the expression, this expression for figure of merit, right? Where Kf is the frequency sensitivity constant, P is the signal power, and W is the bandwidth of the original modulating signal. Friends, I hope you like the video. In case you have any doubt, please feel free to drop in comment box. Thank you for watching my video.